Okay, here are your 3 bonus worked out problems with a video. Normally you might have gone through these in the tutorial, but I'm going to provide a video for you to go through these. We have 3 separate beams. This is our first one. This is beam 1. And we want to know what RL and RR need to be for this to be in equilibrium. So before I calculate anything, I always ask myself, what end do I think will be higher? Do you think RL will have more load or RR will have more load? Well, look, intuitively, I think most of the load is going to come down here to this end. So I'll often write myself a little note that, yeah, I think RR should be greater than RL. Probably by quite a bit. I'm not quite sure how much, but definitely by a significant amount, RR should be higher. So let's go through and use those equations that we talked about in the lecture, where we can sum the forces in the x direction, sum the forces in the y direction, and sum the moments about any point in this system and have this be in equilibrium. And then we can see if that'll help us solve our reactions. So let's make the paper bigger, and we'll go through this problem. My camera's just a little bit crooked there, and it drives me bonkers. There, okay, so now my paper can be straight. All right, so we have our very first problem here. We have each one of these loads is 2 meters apart. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. Okay. So we are going to draw 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have our beam here. There is an applied load of 4 kilonewtons. 6. I'm going to stop writing the kilonewtons. They're all in kilonewtons. Sorry, this was 5. 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All of these are in kilonewtons, pushing downwards. We don't know what the reactions are here. I probably should have drawn this, but most beams are a pin roller support. This is our unknown Rx. This is our unknown R at the left end of the beam, and our unknown reaction at the right end of the beam. Every single one of these is 2 meters apart. So every one of these distances was 2 meters. All right, let's start by summing our forces in the x direction, where everything in that direction is positive. Well, we've got our x equals 0. There's no applied loads, so that actually doesn't take any load. Let's sum our forces in the y direction, where everything upwards is positive. And we want to know what it takes for this to be in equilibrium, or we want to know that this thing is in equilibrium. So we've got all of these forces acting downwards. So we've got -4, -5, -6, -7, -8, -9, -10, -11, -12, -13, -14. We have our unknown RL upwards, and we have our unknown RR upwards. So plus RL plus RR, and we want to know what it takes for this to be in equilibrium, or we want the sum of all of these to be equal to 0. Well, we can add all of this up, but we're still left with RL and RR. We have two unknowns in one equation. So let's add this up. 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 equals 99. Or RL plus RR equals 99 kilonewtons. So the total load coming downwards on this beam is 99 kilonewtons, and some division of load between RL and RR equals 99 kilonewtons. But we don't know how much goes to each side. Let's sum our moments about the z-axis, where everything in this direction is positive, and we want to know that this thing is in equilibrium, or we want it to be in equilibrium. How do we pick what point to spin about? Well, I'm going to tell you, I am a lazy person. And unless there's a good reason not to, for a simply supported beam finding the reactions, I'm always going to pick my left reaction right here, because I'm lazy. It's just what I'm going to do. So, picking this point right here, RL passes right through the node. To be a moment, you have to have a force and a distance. Well, RL has no distance, so it doesn't try to cause this beam to spin about this point right here. Remember, I'm putting my thumbtack here. Rx doesn't try to cause it to spin, and our 4 kilonewtons also doesn't try to cause it to spin. 5 kilonewtons does, 6, all the way up to 14. Every single one of these tries to spin it in this direction. Let's curl our fingers in that direction and then point our thumb. Well, every single one of these tries to spin it in the negative direction. Our R tries to spin it in that direction. Let's curl our fingers in that direction and use our thumb. Our R tries to spin it in the positive direction. So remember, you need a force and a distance to be a moment. So the distance away every single one of these is how we calculate our moment. Let's look at 5. We know all of these are causing a negative moment. So minus 5 times 2 meters. Minus 6 times 4 meters. Minus 7 times 6 meters. Minus 8 times 8 meters. Minus 9 times 10 meters. Minus 10 times 12 meters. Let's double check. 2, 4, 6, 8, 10, 12. Minus 11 times 14 meters. Minus 12 times 16 meters. Minus 13 times 18 meters. Minus 14 times 20 meters. And then we had our RR, which was positive. RR times 20 meters, because it's 20 meters away, equals 0. All right, there's only, as long as this equation is, only one unknown, RR. All of this can be calculated and brought to the other side and then divided by 20. Let's take a look at that. When we bring all of these to the other side, they'll be positive. So we have 5 times 2 plus 3 times 4 plus 4 times, okay, I'm going to have to do this slowly. Okay, 5 times 2 plus 6 times 4 plus 7 times 6 plus 8 times 8 plus 9 times 10 plus 10 times 12 plus 11 times 14 plus 12 times 16 plus 13 times 18 plus 14 times 20 divided by 20 equals RR equals 60.5 kilonewtons. So for this thing not to spin about this point here, RR has to equal 60.5 kilonewtons. Well, now we know what RR is. We can figure out that RL plus 60.5 equals 99, which means that RL equals 99 minus 60.5, or 38.5 kilonewtons. Remember back at the beginning, we guessed that RR would be a higher load than RL. And look at that, 60.5 and 38.5. Most of the load is being supported at RR, and for this thing not to move up and down, slide back and forth, or spin in space, we need our reactions to be 60.5 at the right end and 38.5 at the left end. So we have just solved for the reactions of our very first beam. Let's take a look at this diving board. Okay, so for this one, we have our unknown reactions and somebody standing out here at the end. What do you think is going to happen with this? If we had, pick up a ruler if you'd like, and hold it on your fingers, and then put an eraser at the end of the ruler, and see what happens. Don't hold the ruler down. You know that the ruler is going to try to tip. So you need to do something to hold on to the end of the ruler. You have to grab the end of that ruler to stop this end from kicking up. This is because you understand that we are trying to spin it about this point, and this is trying to make it spin, and we're going to need something to hold it down here to stop it from spinning. But it doesn't matter. We don't have to pick that point to spin this about to figure out what these values are, because if it's not spinning here, if we're holding this down in some way so it doesn't spin about this point, we can talk about it as if it was trying to spin about this point, because it's not spinning, or we're trying to figure out what it takes for it not to spin about any point in the world. So let's take a look at our diving board example. All right, so we have RL, right here. All right, and this is RR, and we have a load right out here of 1.5 kilonewtons, and they have told us the dimensions are 1.2 meters and 0.4 meters. So I've just converted, oh, you know what's going to help you guys? I'll pull this up here like this. So I've just converted this to meters because I know it's going to be handy to talk about this in kilonewtons and meters. Okay, let's sum our forces, sum the forces in the x direction where everything in that direction is positive. Rx equals 0. We're getting used to that right now. We don't have to worry about that too often. We will do problems next week where there might be an applied load and Rx doesn't equal 0. But there's no applied load here right now, so we're not too worried about that. Let's sum our forces in the y direction, where everything upwards is positive. We have RL going upwards, and RR going upwards, and our 1.5 kilonewtons going downwards, which is negative. RL plus RR equals 1.5 kilonewtons. So those two added up have to equal 1.5 kilonewtons, but we don't know what their individual component is. Let's sum the moments about the z-axis, where everything in that direction is positive, and we want to know what it takes to be in equilibrium. And I have told you I'm lazy. I always pick point right there to spin my points about, even though it doesn't matter what point we pick, because this, we want it to be in equilibrium. And for it to be in equilibrium, it can't spin about any point. So we can pick the point we want to talk about as long as this is in equilibrium. And that's what we want to figure out. What does it take for this to be in equilibrium? So if I pick this point right here, and I am saying that everything is trying to spin it about this point, our L passes right through the node. So there's no eccentricity, which means it doesn't cause it to spin. Our X passes through the node, which means there is no eccentricity, which means nothing that it doesn't cause it to spin. Our R tries to push our paper in that direction. It tries to make it spin in that direction. Knowing it's spinning in this direction, curling our fingers, our thumb tells us that that is a positive moment. So plus RR times its eccentricity, which is 1.2 meters. We have our 1.5 kilonewtons trying to spin it in that direction. If we curl our fingers in the direction it's trying to spin, our thumb tells us that it is a negative value because our thumb is pointing into the page, or minus 1.5 times, we're talking about this point here, so it is 1.2 plus 0.4, or 1.6, equals 0. We want to know what it takes for this to equal 0. We have an unknown here, so we can figure out what our R would need to be to make it actually equal 0. So we have 1.5 times 1.6. It was negative. We bring it over here. It makes it positive, and we divide it by 1.2. And we get that R equals 2.0 kilonewtons. Great. We have a value now. Well, now we can plug this in here. RL plus 2.0 equals 1.5. RL equals, minus 0.5 kilonewtons. That is telling us that this arrow is wrong. I guessed that this was positive, but it turns out it is in fact not positive. It is a negative value. That means this force is acting downwards, or it's the thing trying to hold the back end of this down. I'm going to redraw this free body diagram two ways with all of the information filled in on it. We have Rx equals 0. We have our arrow here of minus 0.5 kilonewtons, 1.5 kilonewtons, and an applied load, sorry, that was 2 kilonewtons, my mistake, 2 kilonewtons, and 1.5 kilonewtons. All of our distances are 1.2 and 0.4. No, I think there's more. 1.2 and 0.4, and our applied load, 5 kilonewtons. That's 0. That is 2.0 kilonewtons. 0.5 kilonewtons. These two things are equal. We can keep drawing the arrow upwards and indicate that the value was a negative number. We can change the direction of the arrow and now start writing it as positive because the arrow is indicating that we're trying to hold it down. This says that we have an arrow going upwards, but the value is minus 0.5, which means it's acting downwards. So these two things are the exact same free body diagram. Let's do this same problem where we shorten the backspan. Let's make this backspan a little bit shorter. So I'm going to do this one just a little bit faster now. So now we've got .4 meters and 0.4 meters. We've got the same applied load we had before of 1.5 kilonewtons. And we have a reaction RR and a reaction RL and Rx. We want to find out what Rx, RL, and RR need to be to keep this in equilibrium. Let's sum the forces in the x direction, where everything in that direction is positive, and we want to know what it takes for this to be in equilibrium. Rx equals 0. I'm just going to do things in a slightly different order now. I've been finding RR as one unknown in one equation. I am going to spin about this point now. I'm just going to do them in a slightly different order. Same thing, same equations, but now I am going to sum my moments about the z-axis. I want to know what it takes to be in equilibrium, and that direction is positive in our world. And I am going to spin this about my right or my left reaction. I'm putting my pin right there. So if I put my pin right there, RL acts through it, Rx acts through it, so the only thing causing it to spin are RL and our 1.5 kilonewtons. RR is trying to make it spin in that direction. My thumb tells me that is a positive moment. So RR is trying to spin it in the positive direction, and its distance away is 0.4 meters. My 1.5 kilonewtons is trying to spin it in that direction, or it's trying to spin it like that, and we have a negative value because my thumb is pointing into the page, or minus 1.5 times 0.8 meters. We want to know what it takes for this to be in equilibrium. We can rearrange this. 1.5 times 0.8 divided by 0.4. RR equals 3 kilonewtons. Now, let's sum the forces in the y direction with everything upwards being positive. We've got RL, which we don't know what it is. We've got RR, which we know is 3 kilonewtons. And we've got our 1.5 kilonewtons downwards. That tells us that, and we want that all to be 0, RL equals minus 1.5 kilonewtons. Or, we now have a free body diagram that we can draw if we wanted to as 1.5 kilonewtons, .0 kilonewtons, and 1.5 kilonewtons. You don't always have to draw it to scale. The magnitude can indicate your scale. I'm just trying to show you. Oh, I didn't draw this. Let's just redraw this here. 1, 2, 3. 1, 2, 3. 1.5 kilonewtons. .5 kilonewtons, and 3.0 kilonewtons. So this actually makes sense. You can see if these are equal distance apart, it's kind of like our teeter-totter. If this distance is the same, we need two things acting in that direction. So this looks exactly like our teeter-totter situation that we had before, but instead of being a person standing there, we need something holding this down for that value. So these are the bonus examples I wanted to do for you. So hopefully this has given you a bit of practice and you can enjoy your tutorial.